reduce things like bacterial deposition, fibrosis, which is scar tissue formation around devices, and thrombosis, which is blood clotting. So this unique chemistry can resist those different types of biological pathways, we call them. Okay, so our company began our journey with the fight against infection. And in the US, a lot of these patients go into the hospital for a device. That device gets infected and they have to come back or leave or stay in the healthcare facility for much longer because of a device complication. This might be infection, could be blood clotting, it could also be things like the foreign body response, which I know is an issue with cochlear implants for long-term use. There's also a large financial burden as well, so very costly to the healthcare system just here in the US to deal with these types of complications. Okay, so I'll kind of go through this quickly, but antibiotics have traditionally been used to address things like infection. And this is more of an example of just drugs in general being the fallback position or the main route, I guess, to deal with device-related complications. But we want to move away to get away from the use of antibiotics because we know that antibiotics causes bacterial resistance, which is like we call them superbugs. So these bacterial cells over time get stronger and antibiotics become weaker due to evolution. So we want to find different ways to address device-related complications without the use of drugs, in this case, antibiotics. Also in the last, we'll say 25, 30 years, this idea of how infection begins and reoccurs or happens again and again has changed. And this is really due to synthetic materials or devices that are not human tissue, like silicone and polyurethane and other types of rubbers and plastics. When they're placed in the body, they allow for biofilm to grow on those devices. And this is just I'm showing here the kind of cascade of events, what happens when you place a device in the body. Cells begin to stick to that device and they begin to grow into these communities. And these communities called biofilm, you can think of them like a fortress that protects the cells from the body's immune system, so your body trying to deal with the infection, or drugs. And by stage 5, that biofilm grows to be large and erupts or bursts open, and these cells can go colonize other parts of that surface. So any device implanted in the body can be covered in biofilm very quickly. And once a biofilm has formed, they're very hard to treat. So our goal as a technology and our goal as a company is to apply a surface treatment right here, this thin layer, shown here in blue, a very faint blue stripe, that resists the deposition of these cells to the surface. And without that initial deposition, that initial adhesion to the device surface, you do not get this cascade into these biofilms that can cause a lot of problems. So that's the idea behind the whole technology. And we're doing this without the use of drugs. So I mentioned in the introduction that we use a unique chemistry called zwitterion chemistry. It's highlighted here, zwitterionic surface treatment. We published this paper in 2022, so 3 years ago we published this in Advanced Materials, a very highly respected journal here in the US. And we really introduced the technology for the first time to the public. I also want to point your attention to the third word in this title, scalable. Okay, so scalable is the ability to scale the technology to commercial quantities. And that is a key differentiator, a key point for our technology is we can move this from the academic world and bring this into the commercial world. And no one else before us has been able to do that for several technical and economic reasons. So me and my research team developed a way to deposit this surface treatment to materials like silicone at a very high level in high quantities to produce products. That's essentially the value of our company right there. The chemistry, the zwitterionic chemistry, we are making, you have in every cell in our body, there's a cellular membrane. You may remember from biology, if you studied biology back in college or university. Every cell is surrounded by this zwitterionic chemistry. So we are inspired by nature to mimic or to copy nature, and that's how the treatment works. So we are making your device, you can think of it more tissue-like. So the body doesn't, the human body doesn't respond to that device as a synthetic material, but more like tissue. And that's the idea behind the coating. Okay, this slide is simply just to show that traditional coating techniques for this material, this zwitterionic chemistry, doesn't work. The material itself is completely soluble in water, so it dissolves in water. And so if you spray on this material onto silicone or some other underlying solid, and you place it in the body, that coating will immediately dissolve away, and so you'll lose your effect, right? The effect will dissolve away with it, and so you'll leave behind your bare coat, your bare material. So what we do, we create covalent bonds or permanent bonds between our coating material and the surface, so it cannot dissolve away. So we call our coating a permanent surface treatment that stays there for the life of the device. And because we can apply this treatment scalably, as we talked about, we can scale this to large quantities. We can do this in the manufacturing setting, which we've done. And we can do this to many, many devices at a time. And so we can meet the demand that your device is currently sold at, or will be currently sold at if you're still in the prototype phase. Our material does not use any things like antibiotics or drugs. And so because we're not killing any bacterial cells or fungal cells, we do not promote resistance when dealing with things just like infection. So it's this new idea where we can resist the deposition of these biological cells like bacteria and fungus, but we're not killing them. We're just preventing them from growing, in a sense. Okay, any questions so far before I move on? Okay, I will continue. So this is some initial data that we produced. We applied the treatment, the zwitterionic or the silk surface treatment, to silicone devices, little discs. And we incubated those discs that have, this is just bare silicone, so no treatment, just bare silicone control discs, versus the discs with our surface technology on it. We placed them in the same environment with different types of bacteria, and you can see the adhesion of those cells all over the uncoated silicone. But with the coated silicone, you can see the effect it has at resisting the deposition of those different strains of bugs. We like to point out this is called, in the US we call it MRSA, which is a resistant bug to some antibiotics. And so it's a physical phenomenon that we can resist the deposition of these bugs without killing them. Okay, we wanted to show the same effect on the inside of devices. This may not be relevant for your device, but for some devices in medicine, they are tubes that go in the body. And so we wanted to mimic, or we want to experiment on what happens on the inside of that tube as well when our treatment is applied. And so we carved out these channels in a block of silicone. We created channels that allows us to circulate different materials through those channels and observe kind of what's going on the inside of the tube. We did that with bacteria that fluoresces, so we can see it under a microscope, just like we did previously on the discs. And we took E. coli bacteria, we pushed them through the channel under flow conditions, and after 24 hours, you can see that the entire channel made out of silicone is covered in biofilm. So tons and tons of bacteria lining the sides, the walls of the channel. We did the same experiment with the zwitterionic surface treatment, the silk surface treatment, and you can observe again the effect on the bottom panels under the same conditions. We observed the same properties with protein. Fibrinogen, this is a protein that's in the body, circulates the blood, so it's in our bloodstream. And if there's any scratching or tearing of tissue in the body, this protein, fibrinogen, is the first to, first to the scene. It goes to that, wherever that trauma is, that tear of the tissue, and it gets cleaved, it gets changed into fibrin, which is blood clotting. So we have good indication that our coating can resist blood clotting as well, not just bacterial adhesion, but also blood clotting. This is what the channel looks like under the microscope, and this is anything in red is that protein depositing to the surface of the silicone channel. And then again, we see complete rinse out of our Zwitterion treated channel. It's completely clear. This is a little bit more complicated, but I'll go through it slowly. So we tested fibroblast cells. These cells, this is from Wikipedia, they create the scar tissue and collagen in our bodies. And when these cells adhere to surfaces, they form these long anchored structures shown here in the picture. You can see that same thing happening. They're circular cells, but after 24 hours, you can see here with the uncoated substrate, those cells forming these elongated structures shown here, just like this. With our surface treatment, again, on the bottom, those circular cells don't elongate, they don't anchor to the surface and stick. They actually stick to themselves. They have nothing to stick to because that surface is protected by the coating. And we have good indication that we can resist things like the foreign body response. When you put a silicone or other type of material in the body, your body responds to it in a certain way. We have good indication that we can resist that response, which may be good for your cochlear implants that may lose signal over time. Yep. Yes, sir. Yes. Yes. Yes, exactly. That what you're describing is the foreign body response. They are two separate uh, things, but they are somewhat related in some aspects. So the biofilm is from bacteria. The foreign body response is from synthetic materials that aren't tissue being placed in the body, and your body responds to those synthetic materials by typically putting a capsule around it. So you make scar tissue around that device as a way to protect your body from that device. But in some cases, the bacterial biofilm causes the body to react a certain way too, to create that capsule as well. It varies device to device, but they are two separate biochemical cascades, we call it. Yes, in some cases, yes, in some cases, device manufacturers want their device to bond to the tissue. A good example is orthopedic implants, where they want that fusion to occur. So our coating is probably not a good solution for orthopedic implants. Yeah. Yes, yes, you're absolutely right. It seems like from our reading, if we can coat your electrodes, that would be the best target. Not the other materials, but if you want some fusion to occur with the tissue. But if you don't want fibrosis to occur on the electrodes, or you want to reduce fibrosis on your electrodes, then it would be a good candidate for our technology. Mhm. It's an additional coating material. So the silicone is a very good material for insulation from the electronic parts, right? The silk is an addition to NuSil silicone that we can apply a very thin treatment on top of NuSil silicone. It's a good marriage between of two materials. Okay, great. So I got one more slide on the fibrosis for you, actually. So the question timing was very good. So we implanted silicone discs, little sheets of silicone in mice for 3 months. And in the top 6 images, 1, 2, 3, 4, 5, 6, this is the tissue in contact with that silicone disc. The silicone material was on the left of these images. We stained the tissue in a stain specific that binds to collagen. And so what we're doing is we're observing collagen growth, which is an indicator of fibrosis on this tissue. And so you can see here in the top 6 images, a lot of blue, a lot of collagen. And that's that capsule forming, that scarring forming around that device. with our treatment in mice for 3 months, 12 weeks, there's still a little bit of collagen right at the interface, right at the next to the device, but the tissue away from the initial capsule is completely healthy. And so we have more good indication here that we can resist fibrosis. And this might be valuable for your electrodes to keep their, to reduce their impedance over time. Okay, we also can reduce the friction of your implant. So the electrode, we know that silicone is quite sticky, or we call it tacky. It's grabs the tissue when it slides in. So with the silk treatment, we're dumping glitter, and you can see the effect of the treatment. It's slippery even when dry, and it slides, the glitter slides right off the face. So another benefit to the treatment on NuSil silicone. Okay, so we know that all medical devices must be very safe. So we performed biocompatibility testing on our treatment on silicone. It passed every test. It's a very safe material. As I mentioned, it mimics or copies the same chemistry as our own body's chemistry. So the material itself is extremely biocompatible. And for our product, we've developed a catheter, a long tube, and we wanted to demonstrate the scalability, right? The ability to do this to many, many units at a time. And so we built this machine that can do a million units per year if we wanted to. And so I'm going to play a short video, a couple minutes, demonstrating kind of the story behind our technology. It'll show you some of the images of this machine, but this machine will not be used for cochlear implants. We will build a much smaller machine for cochlear implants.
Infections, whether contracted in a hospital or through some other means, are a serious problem in terms of patient health and are a multi-billion-dollar burden on the healthcare system. We've used antibiotics to treat them for decades, but the problem is that antibiotics have been overused and bacteria are increasingly able to negate their effect, giving rise to new strains of antibiotic-resistant superbugs. There's an urgent need, therefore, for a solution which addresses the problem of infection at its very core. Silk has developed a groundbreaking treatment technology that can be applied to the surfaces of many implanted medical devices to protect against bacterial aggregation and the growth of biofilm. The treatment is intended to stop infections before they even begin. Furthermore, surfaces treated with silk formulations exhibit enhanced lubricity and reduced tag, which provide greater patient comfort during implant and explant.
Our patented technology is the result of years of research in the field of material science. Our first product to market is a Silk ClearTrack indwelling Foley catheter, which has now been cleared for sale in the US by the FDA. Patients and clinicians report dramatically improved comfort and reduced catheter incrustation and less visits to the clinic due to complications versus other catheters on the market.
We see these complications very frequently. I think that the Silk indwelling Foley catheter has a significant potential to improve the quality of life of patients who use a catheter to manage their bladder and to really decrease the burden on the healthcare system that's associated with catheter complications.
So prior, I was getting constant infections. So I was being hospitalized for infections. There was huge trauma to my bladder. So once we got this catheter, it was heaven sent. I haven't been hospitalized since. I haven't had any infections whatsoever. And this has given me quality of life. And I can see the amount of lives it's changed. It's changed mine in a big way.
We have engineered our treatment to react chemically with many materials to permanently transform their surfaces without modifying their bulk properties. The deposition process is rapid, is performed under ambient conditions, and does not require pre-treatment, exotic reaction equipment, or toxic chemical solvents. This makes it possible to easily scale the treatment to commercial, economically viable levels of production. We are the first company in the world to be able to commercially transform the surface of silicone to create a more favorable interface with the human body. Okay, just wanted to show you that video to kind of show you what we've done with our own products, but we also would like to coat your products and other products. So we've been working with NuSil here, with Ace and his team on working with newer other device manufacturers to apply this technology to their products. Okay, and that is the overview of our technology. So if you have any more questions, I'd be more than happy to field them.
Yeah, let me have a quick question. Have you ever tried to make a coating on any material or metal, like metals, like platinum or titanium?
No, we haven't. Well, our coating will not stick to metals by itself, but we can add a narrow tie layer, a thin layer that allows our coating to bond to metals.
And is it? I think it isn't conductive, right? Electrically conductive, right?
No, but interestingly enough, there's been articles in the academic world about using zwitterions on cochlear implants and these types of coatings, and people have seen the impedance actually reduced for some reason. Yeah, it's quite interesting actually, but it's been talked about. So there might be some ionic conductivity that's going on. I need to look to see if it's published or not, but we've seen some data, and yeah, that's all I can really say about it at this point. Sorry, I'm under non-disclosure with some company. Electrochemical measurements without biological parts. But I believe, yeah, I believe Marlon Hansen, if he hasn't already, he will publish an article demonstrating the effect zwitterions have in vivo. He's out of Iowa University. Yeah, we can modify the thickness, so we have control over the thickness. It's likely going to be between 2 and 3 microns, maybe 2 and 4 or 5 microns thick, depending on, and that's what we, with all of our customers or potential customers, we work together. You know, we sign some agreement, and you tell us what you're looking for, what properties, and we try to match the right properties to what you're looking for. So yeah, but I would imagine in this case it could be probably between 2 and 5 microns. It's a proprietary. I can't talk about it in general, but you can read about it in our article in Advanced Materials. That will give you a sense of what we're doing. It's a liquid process, and we're using UV light, and we can actually coat your finished device. So we can either modify your device before it's finished, or we can actually take the final implant and do this process on it as well. And our business model is building you a machine to put in your facility. So we would train your staff at some point if all the properties are hit to do this in your own facility. You shouldn't detect any differences in the flexibility. It doesn't, so it's not silicone. Silicone you can stretch. It can't stretch like silicone can, but you can bend it. You can put it around a radius. Yeah, it holds up to normal use in the body. So it's hard to say because that would be mostly your device because the coating is so thin. It's the Young's modulus. It has to go on something. It can't just be its own standalone material. Yeah, so we'd have to deposit it on some substrate, and then we'd have to test on that substrate. So the Young's modulus would likely come from the silicone or whatever material you're using. Yeah, I do. I think it'll do just fine, unless you're taking sandpaper, you're scratching at the surface hard. But if you're simply just bending it around a radius, it could be fine, unless it's being crazy.
No. Actually, it should be done in for the lead wires, not the electrode part. Yes, yes.
Yeah. Also, I imagine that if you took an electrode with your lead wires and you stretched it, you would destroy your lead wires as well, right? So. Yeah. Oh, okay. Very nice. Correct. It will selectively go after the silicone and not the metal. It's good for us because in our machinery, we can use metal during the coating process and it won't bind to the metal. So we don't have all this coating everywhere in our machine. So yeah, it helps us often in our machine design.
But I'm afraid that if we coat a whole electrode body, including electrodes and the body, the encapsulations, silicon, yeah, the benchtop test of the result of the benchtop test seems very good, and what I'm afraid of is that after the coating, the coating will be coated on only on the silicons. Then, if it is applied to the immune response body environment, then the silicon can be protected from the schist schist you told. But on the electrode, I'm afraid that only the schist schist could be formed only on the electrode. So, yeah, have you ever tried the biological test with the coatings in both surfaces? I mean, both metal and silicon surfaces.
No, we don't have any electrode specific tests at this time. Maybe something that we can do with you if interested to pursue the project to see how the electrode plus our coating can do in some sort of animal, some sort of model that we can do. That would be something very interesting to see. But so far, it seems like this coating would be a good candidate for cochlear implants. And I think that the reason for this meeting is for that. Yeah.
Yeah, actually, it can be protected by giving the electrical stimulation on the electrode. So yeah, that's just my concern. I think it will be very good. Yeah.
It also can help the electrode slide in to the
Mhm.
cochlea much easier,
Mhm.
much less friction, which
Yeah.
may prevent the foreign body response as well, because that trauma might trigger the foreign body response.
Yeah, that seems very excellent. And yeah, what we have to do is that just packaging our products to you if we want to try the techniques.
Yeah, of course. I mean, we need to get an agreement in place, a confidentiality agreement. But yeah, with most of our customers, we trade samples. You can send samples, we coat them, we send them back to you. We'd like to know how they're tested. I would suggest maybe doing a friction test to start to see how it does in a cochlear model. But yeah, that would be kind of how we typically work with our customers.
Interesting.
It's a general chemistry. Let's see if I can find an old presentation I can show you. If my computer will cooperate. Okay. Okay. Those zwitterions are simply mixed charged materials. So this has a positive and negatively charged group on it. You remember back from organic chemistry a long time ago. Amino acids are zwitterionic. I'm also showing the same image here. They have a equal charge, so they're actually neutral. They are neutral, but they are charged at the same time. And they're very good at resisting other things. Amino acids, you might ask, why don't I just coat amino acids on the implant, on the electrode? Well, amino acids would dissolve in water, so they go away. So that's the challenge, is how do you get these things to stick to the surface? Yeah, and I can send you lots of articles about all the research done on zwitterions. Here's here's a question about the foreign body response. So here's the cascade of encapsulation. So protein absorption is first, and then this. So I showed you this slide, and then blood clotting as well. And then all these papers on different, you can almost type in any implant you can think about on Google. Or put the word zwitterion after, and you will find a lot of research articles on each implant. That's our material, yeah. I think we have the only one right now. There's a lot of small companies like ours trying to do this zwitterion, we call it zwitterate materials. The thing that my research team did was the anchoring, the ability to modify silicone permanently. And that is spelled out in the advanced materials paper. The challenge is with silicone specifically. It's a very tough material to coat. Imagine painting a rubber. It just doesn't, it delaminates just like that. So that's the challenge that we overcame. It's, yeah, with a few changes, but yeah, that's the backbone of it. It's a secret. That's in all of our patents have that. Yeah. So I know it in here, but yeah. But it's a general structure we're showing of, because in the academic world you can't just say you did something. You have to show kind of what you know how you got there. So. Sure. Yes. So hydrophilic, this is a good question because there's a lot of hydrophilic coating companies. Hydrophilic they cannot boast the biological improvements that we can. The Zwitteron is specific to preventing biofilm, thrombosis, and fibrosis. In some cases, hydrophilic coatings cause those things to occur. It depends on the chemistry of that coating. And yeah, if you're interested, I can send you this article. It came out in 2021, so 4 years ago. Trying to solve this issue of the foreign body response. And this is where I got this image from. And they say here, I believe, yeah, so even polyethylene glycol, very common hydrophilic coating, or polyhema, polyethylene, and cross-linked collagen, they're widely used and considered to be biocompatible materials, have been reported to induce FBR, foreign body response. Okay, so it's very chemical specific. And the first material that people are seeking are new materials to resist FBR. Zwitterons. So if you want me, I can send you this article as well. It's very, very good article. Okay, any other questions about the technology, the presentation, the business?
Yeah, I think we have to figure out how to make any trial with your technology, and definitely I'm intrigued by yours. Yeah, so do we have to contact to TJ to make any progress on the project, or do we have to contact you directly?
I would go through NuSil, through Ace and DJ. They're the points of contact. They introduce us to, and but we work very collaboratively with NuSil. So you see me on the contact, we can all have a big conversation. So
Yeah, that's very good for you. And yeah, as you already as you may know, we are just a startup in our industry, and yeah, we are trying to make some differences from other competitors in the cochlear implant. So yeah, I think we can. As far as I know, many cochlear implant companies are interested in your technology. So yeah, we have to follow the stream. I think so. Yes. Thank you for your presentation, and it was very interesting and yeah, just excellent technology.
Thank you. Yes. It would have to be an individual submission. So it couldn't be just, hey, we use their material and we use ours, so it should be approved. But it always helps with the FDA and the other regulatory agencies to already have some predicate to say, hey, we've already done it in this device, or we've done it on several devices. So for the FDA to look at that and say, okay, other devices are on the market, there's no major issues, this should be okay. So and the other thing that, in my opinion, there's some companies that are trying to put drugs into their devices, and that is a regulatory nightmare to show you have a drug coming out. With our coding, it's in my opinion, much more straightforward, that you have two separate materials, you marry them, you show that they're both safe, you show that the combination is safe, and then hopefully the regulators approve the product. Sure.
Thank you. I'm looking forward to having progress on this project. Yeah. Thank you anyway.
Thank
Yeah.
you.
Of course. Thank you. Nice to meet you. And thank you, DJ and Ace, for setting up the meeting.
Absolutely.
Yep.
And we can, DJ, we should work together to put a trilateral NDA in place so we can further the conversation.
Yeah. By the way, don't you have any questions about our company or our technology? Maybe the cochlear implant is already known to everyone, right?
Before starting this session, actually, I shared the background of Toda. When we are working with Lucille, so those guys are aware about Toda, but not 100%. But just the Lucille point of view, I shared the Toda history and what they are doing and what they are doing to achieve. So, but not in specific. So, it's a time limited. Maybe because from today, it's just kind of a good trigger to develop our communication, our relationship. So once something going on like a TNDA, maybe we have more chance to discuss each other. So if you don't mind, it's just let's start this the first step today.
Yeah, good.
TJ practiced well, so.
Thank you.
Okay, then thank you, gentlemen and ladies. So yeah, it is very good time for us. So once this session, I will reach out to Toda to get their video RLP, and then so I will bring to their request to our internal team and Ace and Brian. So yeah, let's develop this communication from now on. Yeah, thank you very much today.
Yeah, thank you.
All right. Thank you, everyone. Have a nice one.
Thank you.
Bye bye.
감사합니다.
바이바이.
내십시오. 네, 연락드리겠습니다. 네.
감사합니다.